All right, let's talk about one-tailed and two-tailed hypotheses. So these have to do with the distribution we talked about and this rare outcome that can occur in these tails, this probability of error occurring less than 5% of the time. Remember, this is common and this is rare out here. Well, it turns out we can split that 5%, and notice where the cutoff is here. We can split that 5% into the two tails, or we can put it all in one tail. Notice the cutoff is over here. The cutoff is further to the middle here in a one-tailed test than it is in a two-tailed test, because we're putting all of the 5% into one tail rather than into two tails. So this directly relates to the way we write a hypothesis. So if we write a research hypothesis that predicts a direction, cancer drug is going to reduce, sorry, I don't have a reduced tail here, cancer drug is going to reduce cancer, we'd want it all in this tail. Or say you're designed a drug that's going to stimulate cognitive ability and people are going to be smarter. You would want it all here. This drug, you want to make them smarter. There you go. It's going to all be in this upper tail. That's called a directional hypothesis or a one-tailed hypothesis. When you're predicting the outcome, you're predicting which tail the results will fall in. If you don't predict an outcome, it's called a two-tailed hypothesis. And it would be interesting no matter which tail they found out. Say you want to see if ginkgo improves memory. And you don't know. It might improve memory. It might lessen memory. So a two-tailed hypothesis is good for you. We'd like to see if ginkgo affects memory. You see how it doesn't predict one direction or another? That's called a two-tailed test. So you have a two-tailed test that does not predict a direct outcome, and you have one-tailed tests, one-tailed hypotheses that do predict outcomes.